Okay. So you're going to get two products in the hydration of both of these. So here, you're going to have 1, 2, 3, 4, 5, 6, 7 carbons. So you're going to have 7 carbons. And you're going to have 7 carbons. Okay. You're going to have a methyl group at 3. And you're going to have a methyl group at 3. Okay. So all I did was redraw that thing. Are we tracking? And if you don't believe me, 1, 2, 3, 4, 5, 6, 7. Should be a methyl group coming off at 3. My alkene was between 3 and 4. There's 7 carbons. So if I were to ask you to name this, it's going to be 3-methyl hepthrene or 3-heptene. Okay? That's its name. So that tells me that my hydration is going to go between the alkene. These are my handles. These are my sp2 carbons. So one of my hydroxyl groups is going to go there. The other is going to go there. So those are my two products. Which of those is major? Yeah, this is major. Okay? If it helps you, I'm fine to do it this way. Okay? That's where you're putting the water. The water that you added is the water of the hydration reaction. And this blue one is going to have the water flipped. It's going to be H, OH. So that's going to put the OH here and the H here. Okay, so those are your two products under hydration of an alkene. All right? Here, I'm going to put the OH this way or the OH this way. So I'm going to have two products. I'm going to have a hydration product that looks like this and a hydration product that looks like that. Okay? Good? Okay. So that brings us back into really what we're talking about, and that is alcohols. And we learned how to name alcohols. We learned about alcohols. One of the things with alcohols is they're very polar. They love water. And the reason why they love water so much because they have and by the way, R is a generic carbon group. Okay, so we use R. We use R to signify that could be a methyl, that could be an ethyl, that could be an aryl, that could be a propyl. It's just some carbon group. All right? It's just a way of making it a generic alcohol. So a generic alcohol loves water. Why do they love water so much? Well, they love water because they kind of mimic water. So when water sees this, it's going to do this. Okay? And if you remember, there are two functional groups that hydrogen bond. We talked about these OHs and NHs. Whenever you see an OH and an NH, you think special because it hydrogen bonds. So here, I'm going to have a really nice bond between the electron pair and the hydrogen and the electron pair of water and the hydrogen. For that reason, water and alcohols really like each other. In fact, ethyl alcohol, so if I don't make a generic alcohol, but I make a specific alcohol, ethyl alcohol, which looks like this, likes water so much that even when you distill it under very careful conditions called fractionating distillation, you still only get 95% ethyl alcohol, 5% water, okay? Which was why back in the day they had things like Jungle Juice and Everclear, which were 181. That's the most alcohol you could get off without doing some really tricky chemistry, which we call azeotropic distillation. And you can actually get it to 200 proof. It's just really difficult to do it. You have to actually azeotrope it off of benzene. So that's how much it likes water. So methyl alcohol loves water. Ethyl alcohol loves water. Propyl alcohol loves water. Butyl alcohol likes water. Once you get to pentanol, you've now crossed over to insoluble. So these are all soluble. This is insoluble. Okay? And here's why. Think of this. You've got this big, greasy, non-polar region of the molecule, right? And so when we get to 5, the grease overrides the polar, and it becomes insoluble. Okay? So at pentanol, you actually start to see 2 layers form. Okay? All right. Now, the last functional group that we're going to see before we move on into some really cool chemistry with aldehydes and ketones is the thiol group. So the group here, so again, this is a thiol. Okay, thiol. So we name these something like this is going to be 1 thiol. 1 thiol. And the thing about thiol groups is they are incredibly pungent. There's some really neat chemistry that we're learning about these compounds. This compound here, methane thiol, this is found in cheese, like your really strong, pungent cheeses, like your Roquefort and your blue cheese, and some of those that smell like the stuff that's on inside of your sink. They're just really, really pungent. Okay. This is the lacrimator in onions. The reason why you cry when you cut up onions. It's a really volatile thiol compound, and it actually it engages the tear ducts. All right. This is found in garlic. It's an antifungal. It's a really, really good, healthy compound to eat. That's why we're learning so much about garlic and its natural antimicrobial properties. It's very healthy. One of the most healthy diets on earth is the Mediterranean diet, which is a lot of tomatoes and garlic. The second most healthy diet is the Okinawan diet, which is a lot of fish and rice. So we're learning a lot about nutrition from just the organic chemistry that we're seeing. One of my favorite compounds is this one here. Check this out. This guy here is, okay, so this is going to be trans. So if I were to draw this out, I better do this. Trans 1, 2, trans, actually 1, 2, 2 butene 1 thiol. That's that compound there. This is a really cool compound. This is the compound that is the main component of skunk spray. And here's the crazy thing with thiols. Within the nasal passage, the receptors that pick up the skunk spray are also that pick up other flavonoids that come out of things like wine and coffee. Wine is said to have about 40 or 400 unique flavors and aromas that come out of it. Coffee is actually over 800. Coffee is much more robust than in its flavor profile than wine. That's why I actually do in organic chemistry, I actually do a coffee lab. And I teach the students in organic chemistry how to actually brew coffee correctly. It has to be the right temperature, it has to be on the bean the right amount of time, it has to be the right bean. I don't know, so much to coffee. There's so much that makes coffee bad, and there's so much that makes coffee good. But here's the cool thing. Next time you smell a real juicy roadkill, like skunk, okay? Roll your windows down. As you smell the skunk, kid you not, try this. As you smell the skunk, think coffee. Try it. you're going to smell coffee. Coffee has a lot of thiols in it, a lot of thiol aromas in it. It's a very aroma. Sometimes we think it stinks, but if you think coffee when you hit a good roadkill, it's going to smell like a really good espresso dark roast. Okay? Trust me. Can't wait. Every time I see a skunk roadkill, man, it's like, kids, roll the window down. Quick, 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 smell. Oh, smells like about a dark French roast right there. Okay? Try it, seriously. You'll be rewarded with the pleasure of a really good coffee. All right? Now, what does an odorless gas smell like? I'm not saying like, what does purple taste like, right? It's the wrong. It's like, can you weigh a chicken with a yardstick? No, it's the wrong context. But here's the kind of the conundrum with the thiol thing. Gas doesn't typically have an odor, all right? So we use methane gas, we use propane gas. These gases don't have, they're odorless. But you're thinking, Dr. A, I've smelled propane before. I've smelled when I turned the blue valve in the chem lab. It has a real strong odor. And I would say it has no odor. And you know how we do that? How we get it to have a gas odor? We actually put a thiol compound in it at about 1 part per 100,000. These are so strong that it doesn't take much in order to detect it by the nasal passage, okay? And that's what we do. We actually put thiols into our gases so that we're not just, somebody leaves a gas line on, we don't even know it because you wouldn't smell it. They don't have an odor. So what you're actually smelling, when you smell propane or you're smelling one of these natural gases, you're actually smelling something that's been added to the gas for safety. Yeah.
Isn't that why a lot of folks in the early days of gas died? Because they weren't putting in anything so they couldn't detect it?
That's exactly right.
Yeah.
And right, so if you accidentally have a stew on simmer, right, and it goes out while you're gone, you're at the store, and you come back, you didn't realize the burner had gone out, you don't smell gas, and you light your cigarette, the whole house blows up, right? So it's kind of a problem. So that's why we put that artificial smell into it, even though those gases don't have smells. Kind of cool. Okay, so that's your thiol family. Thiols are very important. Where we're going to see thiol, we're going to see the thiol in a very important amino acid. There's 2 amino acids of the 20 amino acids of the 20 building blocks of life. We're going to see how awesome they are and that they can spell words like chemistry. You have this amino acid. Okay. And I'll just talk about this one for now. I don't want to make it as Witter. I'll leave it in its natural form. Okay. This is called cysteine. Cysteine. I don't think it has an E at the end. Cysteine, is that right? Cysteine? Oh, that's it. No, it's better. Anyway, spell it. I don't know how to spell. Still don't. I don't want to know how to spell. Cysteine, okay? Because I know it as this. I know it as C. That's typically what we think of it as cysteine. So cysteine is a very important amino acid in that it has this thiol group out here. And what's going to happen is the thiol group is going to react with another thiol group and form a really strong bond. Okay? And so we're going to see this is called a sulfide bridge. Very important, probably the most important feature of thiols for us. Not necessarily their nomenclature. Their physical properties are kind of cool just because they do have all these natural aromas and antimicrobials. But this one becomes very important. When we come back to the 20 amino acids, cysteine is CH2SH. Okay? And we're going to memorize the 20 amino acids. One of the few things that we memorize in here, but that is a very important one. And I will come back to that in a few weeks when we get into amino acids and protein synthesis. Okay? Now, before we jump on over into ketones and aldehydes, which is going to be super fun, I want to explain to you the importance of the phenol. The phenol functional group, if you remember back to our aromatic, this is called a phenol. Okay? And phenols have a much different profile. They're more acidic than alcohols. And if you remember, acidic means the readily availability of that hydrogen to come off the O. So what can happen with this is if I add a phenol to water, what I can get is a conjugate acid conjugate base reaction. And we see this here. Okay? This is really an important property of a phenol. And equilibrium, if we're going to go back to our relation here, it lies heavily that side. It does lie to the left. But nonetheless, that proton, that hydrogen, that acid can come off the phenol. And because of that, we end up with a really important functional group. In fact, if you've ever heard of Lister, he was one of the very first people to ever work with anesthetics and ways to keep microbes down with surgical instruments. And so today we have compounds like Listerine, we have these compounds like Lysol, we have these compounds that, like this one here, is a resorcinol that we actually have in like throat sprays. I don't know if you've ever had like a really bad sore throat, you spray that garbage in your throat and it's supposed to take the sore throat away. Okay, that's what's in there. That's what's actually causing this, all right? So we have two different forms of the phenol. We have a catechol, and we have a resorcinol, and we have a hydroquinone, which is this one here. Okay, these are all hydroquinone. Those are a family of hydroxyl phenols that have special names. So you see this as a resorcinol. When we looked at dopamine, dopamine is a catechol. So that's dopamine. You can see the catechol nature of dopamine. All right, resorcinol and catechol. So especially since we're in like this world of sanitation, a lot of the ones that are using Lysol to remove bacteria and microbes and pathogens, things we don't want around, you're going to have a series. Lysol, for example, is a combination of these two. These are really nice antiseptics. You're going to have that in with some of this. You have two things going on with Lysol. But the whole important thing is Lysol. So that's Lysol. There's a mixture of those two that kill germs, kill bacteria, kill things that are on surfaces. All right? And that's very important. Like I was talking earlier, soap does not kill germs. Soap removes grease. Okay, it's what's added to the soap, the temperature of the water, the agitation, the amount of time that you spend scrubbing is what removes the bugs. All right? If it has this in it, yeah, that's going to remove bugs. A lot of times I'll actually just spray bleach on my hands and wash my hands with a dilute bleach. Yeah.
What's the name of the one?
This guy here is resorcinol. Thank you. You read that? Resor. That's a C, not an E. Resorcinol. Okay? So the phenol family, again, we see it all through the healthcare. We see it within brain chemistry. We see it in forms of medicine. This is in like the throat lozenges that you would have for a sore throat, like with the old ones like Secrets or something, I think they're called. So that would actually take some of the pain away from a sore throat. So you see those all through those. But again, it's the family of these three molecules of the phenol family that become really important from a healthcare, from a chemistry healthcare perspective. Okay? Questions on that?
How do you spell the, oh wait, it is right there, I just behind the monitor.
Resorcinol? Yeah, sorry, it's low. These monitors get in the way. Okay? Okay, so let's review where we've been. Because again, I want to build. We're building. So with this, we've talked about carbon-carbon single bonds, carbon-carbon double bonds, carbon-carbon triple bonds, aromatic. We've talked about alcohols, and we talked about ethers. Okay, you sure we're building? Look at the functional groups we now know. Alkanes, alkenes, alkynes, aromatics, alcohols, ethers. Good? So now what we're going to do is we're going to take the carbon, oxygen, but we've already exhausted carbon single bonded to an oxygen. So now what we're going to do is we're going to say, okay, what happens if in my quantum shell of n equals 2, I take carbon in its ground state, 4 electrons, 4 orbitals, but I only mix 3 of them. Okay, I leave this guy unhybridized. That tells me that I'm only going to have 3 electron domains. 1, 2, 3. So when this mixes, carbon then is going to look like this. It's going to have a 2p that's still unhybridized from here, but it's going to have this sp2. Okay, this is review. This is how we formed the alkene. But in this case, what's going to happen is we're going to bring in over here, we're going to bring in oxygen. Now oxygen looks like this. Okay? Oxygen, going back to chapter 4, oxygen has 8 electrons because it has a blue 8 on the periodic table. So when it mixes, it's going to mix those to form this. Okay? So watch. It's going to have this. Now, oxygen is different than carbon because oxygen already has 2 molecular orbitals that are full. Right? That's because it has 2 more electrons than carbon. So it makes carbon so special, by the way, because it has 4. It can go into what we call a tetrahedron. We're going to learn how that's chiral, which is amazing. So with that, if you go back to something like water, we drew water like this in our tetrahedron, right? It had 2 lone pairs and two lone pairs and 2 bonding pairs. So it still has 2 lone pairs, and it still has room for 2 bonding pairs. But stay with me. One of those is going to be for a single bond. One of those is going to be for a double bond. So what happens with carbon and oxygen when they get together, they form a single bond here. Okay? Gives carbon 2 more bonds, so we can have whatever. We'll just put them coming off. Doesn't matter what they are for now. We'll define those, right? So it has 1, 2, 3 bond. 1, 2, 3 bonds. Oxygen only has room for 1. So it's done because it has its lone pairs out here. Are we tracking? So now I've accounted for. What I haven't accounted for is carbon and oxygen's unhybridized 2p orbital. And we put that here. It's a double bond. Okay? This is called a carbonyl. That is really important. It is probably the most important functional group in organic chemistry as far as the synthesis and a practical application, which is why it becomes very important to understand. I'm showing you where it comes from, but what you need to know is what it is. That is the carbonyl group. Okay? So, we're going to have a bunch of functional groups that have the carbonyl group in it. So the carbonyl, I'm going to use a generic R, because it doesn't matter what's over here on the right, but notice this. If I have a carbonyl, okay, remember carbon has to have 4 bonds, so 3 of them are in the trigonal planar, 1, 2, 3, and it has a double bond to the oxygen. And if you want, you can put the electrons in, you don't need to, but they're up there. So here's the thing. Carbon, if it has a carbonyl and a hydrogen, is an aldehyde. Okay? Carbon, if it has another carbon, not a hydrogen, is a ketone. Carbon, if it's a carbonyl with a hydroxyl group, it's not an alcohol, it's a carboxylic acid. Carbonyl, with not an OH but an OR is good old ester. Is an ester. Carbonyl with a nitrogen. Yeah, let me do that here. These are where we get really fun. Is an amide. That is the bond of life. That bond right there, massively important. That's the bond of life. Carbonyl is an acid chloride. And carbonyl with an O carbonyl is an anhydride. Okay? Now, these are the functional groups we're moving into. We're going to take a little detour through carbohydrates, but this is the complete picture of organic chemistry. Okay? The only thing we need to add to this to be complete is nitrogen carbon, which we'll get to. So, remember, we're only talking about really 3 atoms. We have added some sulfur in there, we've added some chlorine in there, we've added some halogens in there, but for the most part, the majority of what we're talking about, carbon-carbon bonds, carbon-oxygen bonds, and then we'll see carbon-nitrogen bonds. Right now we're moving into a brand new area, so this chapter lands the plane, or crashes the plane, however you want to view it, here. So we're going to look into aldehydes and ketones. We're going to see their chemistry on Wednesday, but today we're just going to work with their physical properties and working with kind of some of the nomenclature with those, okay? We will come back to carboxylic acids and esters, amides and anhydrides, and if we have time, we'll talk about acid chlorides. Okay? All right. So let's talk about aldehydes and ketones. We typically put aldehydes and ketones in the same context, because if you think about it, aldehyde is literally just a terminal ketone. It's a ketone on the end carbon. Okay? So watch. If I just take and put all hydrogens on there, you know this compound. This is called methanol. Okay? You might know it as formaldehyde. That's its common name. All right? Methanol. So what did I just do there? Well, how many carbons do I have? 1. And I say 1 by saying meth. Right? Meth. But it's not methane, it's methanol. So the reason why we don't say methanide, because up to this point, haven't we been using the tail end of the word? So for some reason, we're taking the beginning of the word to make our parent functional group, and here's why. We already have an ide, chloride, bromide, iodide. We already have the ide taken care of. So even though it's an IDE, not a YDE, instead of confusing it, it was decided to go with al. So this is methanol. This is ethanol. This is propanol. This is, what do you think? Yeah, good, butanol. What about that one? What is it? Pentanol, yeah. And here's the thing. Notice, I haven't put any numbers on that, have I? Because by definition, it has to be a carbon 1. If it's not a carbon 1, it's not an aldehyde. So this is why aldehydes and ketones are are related. Okay? So if I take propane, and I put a carbonyl at the end, it's propanal. But if I take propane and I put the carbonyl on the second carbon, it's no longer the terminal carbon. So this is propanone. So we come back to the -one ending for ketones, whereas aldehydes is the al from the beginning, or the first part of the word. So you might know this as acetone. You can see those little red squirt bottles in the lab? Those are all acetone. You might have acetone for fingernail polish remover. It's a great solvent to have around the house for removing gunky stuff. And it's it's a cool sensation, but this is a ketone, okay? So I can't have a non-terminal aldehyde. Aldehydes are always going to be on the end carbon. If it's not on the end carbon, it's a ketone. Okay? So how do I distinguish that? Well, when you get to pentanone, notice. Pentanone, or pentane, can have a terminal carbonyl. Well, that's an aldehyde. That's pentanal. Okay, that's this guy. Or pentane can have the carbonyl one carbon over. So that's going to be called 2-pentanone. Notice this is actually 1-pentanone, but that by definition is an aldehyde. Does that make sense? Okay, it feels like Friday in here. 2-pentanone, all right? What do you think that one's going to be called? Bute? How many carbons? 5. So 3-pentanone. Okay. Isn't that kind of cool? Ish? No? Yeah? Right? Questions? No? So we see these compounds all through. You'll hear words like acidosis, ketosis, these, what's going on within the blood, what's breaking down within the blood. And so what happens with these molecules, the carbonyl functional group here, it's very susceptible to reduction. Okay, we can reduce that down to the alcohol, and that's what we're going to do on Wednesday. We're talking about the actual reactions of these things. I might actually get into it today. But if you draw a molecule, bless you. So we're going to see some pretty elaborate molecules in here. So you're going to get into a family of molecules that starts to look like this. These are called steroids, all right? That's progesterone right there. So we're going to get into the steroid family, but what you're seeing with this is ketone, ketone, which is why it's progesterone, all right? Testosterone actually has an alcohol here, not a ketone. That's the difference, only difference, right? Estrogen actually looks like that. Estrogen looks like this. It actually has a benzene ring. Oh, not even a benzene ring. It has a phenol. That's estrogen, okay? So you're going to start to see these compounds, and why it's important that we understand these functional groups, because they're a major part of life chemistry. All right, these functional groups really do play a huge part of the chemistry of the body, which is where we're headed, because we want to understand enzymes and proteins and how the body navigates the chemical world, uses this pharmacokinetics and pharmacodynamics, what the body does with the molecule, what the molecule does to the body, okay? What happens within that? You'll have that in your pharmacology classes, all right? So, what happens when we start to have multiple functionality on a molecule? Well, check this out. Aldehydes usurp ketones. Aldehydes so far are the highest functional group that we have, which is kind of cool. So we have alcohols, are lower. If they're lower, they have a second name. They call it a hydroxyl. Okay? Next above that is going to be ketones. If there's something higher than a ketone just becomes an oxo. And an aldehyde is the ruler. Okay? It's the highest one. It's an order. I'm doing this in an order of increasing importance. Aldehydes, so far, are the top of the food chain. The very top of the food chain is carboxylic acids, but we'll get there. So if I have a molecule that looks like this, running out of ink. Okay, so if I have a molecule that looks like this, it has both an aldehyde and a ketone. And since it has both an aldehyde and a ketone, I need to know that aldehydes are the parent functional group, are the senior functional group. So this is going to be numbered 1, 2, 3, 4. So when I circle my chain that includes my parent functional group, I call that butanol. Nothing has changed. From rule number 1, finding the longest chain, I added in there that contains the parent functional group, and then I just circle, number, and list all functionality so you can see I have a functional group here. Which functional group do I have? Oh, I have a 3-oxo. So when I put it all together, I have a 3-oxo, 3-oxo butanol. That's kind of cool. See how systematic this is? Makes sense. All right, so your turn. Name this one. Name that. I'm gonna get a new black pen. We have like 5 minutes left. There's not time for me to grab a new pen.
I think is that one has 2 oxygen groups or carbonyl groups. So on the left side is 2 oxygen. Well, it's got it's an aldehyde, so it's or a hydroxyl, so it's or no. It's aldehyde.
Okay, what's the parent functional group on this thing? Alcohol or ketone? Alcohols are below ketones, which are below aldehydes. Ketones. So the parent is going to be a ketone. So I have to circle the longest chain that includes the ketone. So that's going to be here. I have to give the parent the lowest number. 1, 2, 3, 4, 5. So I have a 2-pentanone as my parent. Okay? We get that so far. We see that? Rule number 2, circle, number, and list all functionality. So at 2, I have the parent, so I don't need to, I've already named that. So I have a 4-hydroxyl. So my name is 4-hydroxyl -2-pentanone. Isn't that cool? Yes? Oh, thank you. And there's a 3-methyl. Hi. Great, thank you. And so 3-methyl, alphabetical, goes here. So 3-methyl -4-hydroxyl 2-pentanone. Excellent, thank you. Yes?
Does it not go in alphabetical
Didn't I alphabetize it? Feels like Friday in here. Yes, it does. Try that again. Okay, so it's a charm, right? So 4-hydroxyl, thank you. I know, right? I'm just seeing if you're paying attention. There we go. Okay, that one's correct. All right, not fun? Yeah, super fun. So let me just show you how cool this really is. And I'm not going to hold to this, but but stay with me. We've got 2 minutes left. Watch this. This is why this becomes so important. I'm going to show you something. Okay, let's say we had some monster that looked like this. This is why this systematic way of nomenclature is really powerful. I have a parent functional group, but the aldehyde is the number 1. Right? Yes?
How come you started that aldehyde, not the other one?
What is this?
Uh,
That's what? That's a ketone. Remember, aldehydes have a higher priority.
okay.
They're number 1. They're up here. So you have to get the aldehyde the lowest number.
I'm still not entirely sure how to tell the difference. I don't know. Oh,
This is the branching.
yeah.
Yeah, that's good. That implied thing, it does take a little bit of time to get used to that. So what happens with this then is you just do your rules like this. That's all you do. All right, so this is going to be pent to ene now, pentanal, meaning the 2 is at the ene, okay? And then you just alphabetize, right? You're going to have a fluoro at 3, an oxo or a methyl at 2, and an oxo at 4. Isn't that cool? And again, so it just builds, and it's actually really fascinating how we can name these really complex, different organic molecules with a very systematic attempt or a process of nomenclature. It's kind of cool. Okay.
Then it would be 3-fluoro.
It would be 3-fluoro, 2-methyl, 4-oxo, pentanal, pentene 2-al. Isn't that cool? Okay, on Wednesday, we're going to do probably some of the most difficult chemistry that we're going to do in this class. So I would encourage you to read through the chapter before, because we're actually going to get into the chemistry of aldehydes, ketones, and alcohols. And that's that whole thing of the hydration. That's the kind of stuff we're going to do on Wednesday, but with ketones and aldehydes, okay? So it gets really fun. We're going to talk about oxidation and reduction. So it'd be helpful if you had pre-read that. And yeah, I'll see you on Wednesday, a week from today, or a week from...